seen that when we talk about force, we have Fg is equal to G m1 m2 over r squared, and that force electric is force Coulomb or force electric. Both would be acceptable. KQQ over r squared. Okay? We've already seen this similarity. One of the things that I want to then take a look at is when are the forces weaker, when are they stronger, and what does that mean for the area around an object? So I'm going to take a pair of objects here. Scenario 1, we're going to have object A and object B, position 1, position 2. Okay? First question for you. In terms of gravity, which one of these objects, or which one of these spots, position 1 or position 2, has greater gravitational force? Okay. Greater force. Sure. Okay. All right, let's take a look over here then. Let's say this is some positive charge, some negative charge, some negative charge. 1, 2. Electricity. Which one has greater electric force? 1. Why 1? Radius, it's closer. Okay, we're only talking about the relationship between the big spot and whatever is up, one of the spots up here. We're not talking about how these two are interacting with each other. Okay, go ahead, Habiba. A? Just object A, no one cares what it is. Sure, it's an asteroid. Asteroid for A. Yes, they are. Yes. All right. Next one up then. Which position, 1 or 2, has greater gravitational potential energy? Why? All right. Let's take a look over here. Positive, negative, negative. Which one has greater electric potential energy? Why 2? Same idea as gravity. It's got greater distance to fall. If we want to think about these as having an attractive force, that means they've got some amount of energy due to position. So as these objects would be released into motion, they would both start moving this way. And which one would be moving fastest by the time it got here? Well, that would be this one because it released the most amount of energy. Okay, so again here, greater energy. Okay, now I'm going to change up the scenario just a little bit. Positive, positive, positive. Still position 1, still position 2. Totally a 2. Which one has greater force? Why 1? Because it's closer. And radius is the most important part when determining the force for any of these. So this is greater force. Could be in orbit. Positives, negatives. Really? Okay. Next question. This set, which one has greater energy? These are masses that no one cares. Okay, so again, the question was, which has more energy, 1 or 2? Now the answer is 1. Why is the answer now 1? Okay, so we're now looking at a repulsive force. So this is now greater energy. Okay. When you determined the answer for gravity, regardless of whether it was greater force or greater energy, did the object that I place at this location matter?
Right. If they're the same, no, it doesn't matter at all. So when we look at this, really what we're assessing in terms of these questions is not actually the force or the energy, but rather what we call gravitational field. So gravitational field in terms of Newtonian mechanics, gravitational field is just the acceleration due to gravity of a specific point. Okay, and then gravitational energy. Well, in your conservation of energy unit, how many times did you just cancel out the m from mgh and just worry about the gh value? Basically, every time we did a problem, right? So really, when we're considering which one has greater force, which one has greater energy, we don't really care what the object is here, because if they're the same, they're bringing the same thing to the table. So really what we're considering ourselves with is gravitational field. A gravitational field is, in one way, we can say the local acceleration due to gravity, the local acceleration due to gravity. It is on Earth, yeah. We could also call it the local amount of warp to space-time. Okay. Either way, what we're really looking at is not GMM over R squared, but G is equal to GM1 over R squared, where little g is, of course, on Earth, 9.8 meters per second squared. So one of the other ways we can talk about little g is as the local gravitational field vector. G is the local, gravitational field vector. Okay? So if I wanted to draw the gravitational field around an object such as, say, Earth, E for Earth, no longer A for asteroid, I would draw arrows pointing in towards Earth, showing that it's got a certain amount of gravitational field. And as I go further out from Earth, those arrows would get smaller, showing that as you go further out from Earth, what happens to the acceleration due to gravity? You're fired. There we go. Decreases. Questions about this part for gravity? Yeah. So gravitational field vectors are a sum of the individual gravitational fields of objects. So they kind of add with each other. Right, right. So like if I put the moon here, we'd have some for the moon, and then like in the middle, they'd kind of point weaker, and then towards one slowly more. Okay. All right. So going back up here for electricity. Because we can treat electricity in the same way we treat gravity, we see a lot of parallels between these two. So we've already recognized that the force equations are basically the same. We've already recognized that both exert fields, or are field forces, not force fields, field forces. And they both have similar relationships when we talk about attractive forces. Repulsive is a little different, but attractive ones exhibit the exact same ideas. We can then talk about electric fields. Well, it's almost like gravity and electricity have some sort of relation. Yep. All right. So, talking about an electric field. An electric field is the local amount of electric force that a charge would feel if it was in that location. The amount of force a charge would feel if in that location. It is the local intensity of potential electric. Ooh, I don't want to use potential. It is the local intensity of an electric field at that point. There's no real good analogy for space-time that anyone has come up with. Um, Calculationally, in the same way that we found that mass 2 here did not matter, we find that the charge of the object out here does not change, as long as it is consistent between them, doesn't change which one we would assess as having a greater force or greater energy. And therefore, we can divide that Q out. We can take our Fe over Q2 is equal to KQ over R squared. And this statement is therefore the electric field of our Q1. E is electric field of Q1. Or we could say E as the local electric field vector, meaning that for a charge, let's see here, we would show, just like we do for gravity, the direction of force and magnitude of force based on relative arrow size as an object acts in, or as the field directs in. Fe electric, or C if you want Coulomb force, it both work. This Q is a 2, this Q is a 1. This Q is a 1. 1, 1, 1, 1. 2, 1. Yep. Right. This is a lowercase q.
We were forced to sit in the back, and I couldn't see anything.
When we're looking at gravitational field vectors versus when we're looking at electric field vectors, both represent the strength of a field in a certain location. Both are showing us the amount of force an object would feel depending upon its mass or its electric charge. Go ahead. The field vectors. Yeah. Yep, they're showing the direction of force and the magnitude of force an object would feel at that location. They get weaker as they go out, yes. Oh, no, I just got lazy and I'm not filling in infinite numbers of arrows. Yeah, yeah. Right. I just chose to only draw 4 because I'm not going to take the time to draw 12. Okay. The big difference here for electricity, though, is that with gravity, we only have positive mass. Negative mass is not something that has been discovered or really given much credence to. However, for electric charge, we pretty apparently have both positive and negative charges. So that means that for electric fields, we can draw for a positive charge the opposite direction of arrows. So when drawing electric fields, the arrows should always point in the direction that a positive charge would feel. Direction of force that a positive charge would feel. And you guys saw this on the simulation that you did earlier this week, last week? Whenever it was. Last week. So you guys did the simulation where you had to do the electric field hockey was what it was titled. And when you placed the charges on the map, you saw arrows appear. Those arrows represented the electric field at those locations around the charges. In the same way, these are showing direction of electric field, so did those. There are a few rules for drawing field vectors. So field vector rules. They're very, very, very similar. So there's a slight difference. First of all, electric field vectors flow from positive to negative. So they begin at positive or infinity and end at negative or infinity. So if I have just a negative charge and I remove all positive charge from anywhere within reason, the electric field vectors for a just a negative charge will begin at infinity and extend inwards towards the charge. No? No? I mean, because negative infinity is a direction, and I want to indicate all directions in three-dimensional space. Indicating negative infinity. I mean, if you want to say positive and negative infinity, okay. Begin at positive charges. So, sorry, begin at positive charges or infinity and end at negative charges or infinity. Is that clarification? Right, right. Second rule. Yes. Field vectors are always proportional in number to the size of the charge. Vectors are proportional in number, guys, to the size of the charge. There is an alternative way to do this second one, and your simulation chose the alternative way of drawing this. How did your simulation show the difference in field strength, even though they didn't change the number of charges when you made, or sorry, change the number of arrows when you changed the charge? They faded, yeah, absolutely. So size of arrows or the darkness of the coloring of the arrows is an alternative for this one. So alternatively, opacity and size of arrows. And rule number 3, vectors cannot cross. I can't have two arrows that go like this because they're vectors, they add. So if I were to have two that should cross, they actually recombine into a new one pointing in a new direction. The field vectors are trying to indicate the direction of force that a positive charge would feel at that location. The positive charge, or a positive charge, won't feel force in two directions. It'll feel a sum of the forces in one direction. Right, right. For the purpose of this class and the AP test, and I think even AP2, or sorry, yeah, AP2 is the right statement. Field vectors are a qualitative way of representing a field. Mathematically, it's insane to try to calculate them all. Okay, that's why we have computers. Field is simply the area of influence around an object that it can exert a force in. Okay. Questions about drawing the field vectors, the differences in the positive versus negative ones, or any of the similarities to gravity? So if I've got two charges and I draw the arrows out from them, I have one, right, exactly. Good. Okay, so electric field tells us how much force a charge would feel at a specific location. I forgot to write in a unit here. E is newtons per coulomb. In the same way, we could write little g in what way? I mean units. Units for little g in what way? Newtons per kilogram. Okay. We are also going to take a look at the energy side of things. So I'm going to go ahead and just slide this one up and pull another page out. So extending the dots down. For gravity, we looked a lot at gravitational potential energy as GPE was equal to mgh. And as we stated already, 9 times out of 10, did we really care what the mass of the object was? No, why? Cancels out most of the time. It doesn't matter. Okay? So we routinely looked at GH. GH can also be talked about as gravitational potential. Note, I did not say gravitational potential energy. I said gravitational potential. So gravitational potential, which is equal to GH, is the amount of energy an object would have per kilogram of the object. An amount of energy per kilogram of the object. This is on the left gravity column. Yep. So we could write GH as having units of joules per kilogram. In the same way, we can talk about energy. Electric potential energy, EPE, is going to be equal to, let's see here, Q, E, and then displacement. Now I want to draw that out. So Q is basically the same as electric mass. E and G, we just showed right here, are mathematically similar. H and D, are these very different at all? No, they're both displacement, correct? Okay, so electric potential energy, calculated as QED, is similar to gravitational potential energy, MGH. For most of what we're going to be talking about in this class, we're actually going to just be talking about ED, where electric potential, okay, it was way funnier when he was actually in the class, is equal to ED. All right. And electric potential, therefore, is an amount of energy per coulomb of charge that a charge has. An amount of energy per coulomb of charge.
All right, Connie, we need to fix this chart. The tall people need to be in the back.
I'll just elevate the stools in the back. Telescopes? All right. Guys, with this, last line here that we've got, ED, is measured as a joule per coulomb. And a joule per coulomb actually gets its own unique value, which is a volt.
Oh my God.
I was waiting for it.
Yes.
I mean, it all adds up. It all adds up. All right. This is significant because what we are then talking about with this idea is that a volt is a measure of an amount of energy per charge at a location, which we'll talk a lot more about as we get into current. But for now, that's the notes that we need to cover. Yeah, I know, he's just like freaking out over here. For now, that's all we need to cover.